In section 4.4, we're going to look at the concavity of a graph and also what we call the second derivative test, which is going to be another way to help us look for maximum and minimum points on a function. So if you remember the term concave up, it has to do with the fact that a graph is essentially curving upwards. So informally, if you see a graph that's kind of curving upwards, we say it is concave up. With the calculus, it's really intervals, we should say intervals, where the first derivative, or f prime of x, is increasing. So remember, it means the slope is increasing. So if I look at a graph, let's do one that's concave up. So this one's concave up the whole time. The derivative is increasing. So there's a negative slope, and there's a zero slope, and there's a positive slope, and there's an even more positive slope. So remember, the derivative is just the slopes of the tangent line. So if you look at those tangent lines, you can see that derivative is increasing. But in general, we're going to think of it as making kind of that U-ish shape where it's kind of concaving up. The opposite for concave down is where intervals, where f prime of x is decreasing. So when it's kind of, facing this way, because you can kind of see that those things are getting, so over here they are positive, then they become zero, and then they become even more negative. So concave down. So the way we will check for the criteria for concavity, so we say a graph will concave up when f double prime of x is greater than 0. And we will say the graph will concave down when f double prime of x is less than 0. So we'll similarly make a sign chart like we did for the first derivative. We just make that sign chart for the second derivative. So when we're doing concavity, we're going to try to just start by finding the second derivative, make our chart, and go from there. Okay? So we'll look at an example where we have this graph. This is a parabola, negative 2x squared plus 3x plus 5. So the first thing is I'll find two derivatives. So the first derivative is going to be negative 4x plus 3, but our second derivative just becomes negative 4. So when I'm trying to find my critical points for this, like where the second derivative equals 0, we're essentially figuring out where is negative 4 equal to 0. Well, that's of course never true. So what this means is our graph is always going to be concave up or concave down. So I have no changing points. So essentially it's negative infinity to infinity. So all I'll do is I'll pick a test point, and I will think about whether this graph, or whether the second derivative is positive or negative. So I'll pick 0, because 0 is a nice one. So if I put in 0 for the second derivative, well, the second derivative is always negative 4. It's just negative 4. So it's negative 4. So the second derivative is negative. Well, we said when the second derivative is negative, this graph concaves down. So when we talk about the concavity, it is going to arch down. Now, so it concaves down on the whole domain. So we say it concaves down on negative infinity to infinity. Now, this should be 0% surprising because this is a parabola, and it's a parabola that is upside down. So it's some kind of graph that looks like this. So of course it's going to be concave down all the time. That really shouldn't be very surprising. Other ones will change from up to down, but in general, nothing too crazy. So let's look at another one. So we have x cubed minus 6x plus 9x plus 1. So we want to find two derivatives. So f prime of x is going to be 3x squared minus 12x plus 9. But f double prime of x is going to equal 6x minus 12. Now I would say these second derivatives in this concavity is even easier than increasing decreasing because your power decreases every time, so you're at the second derivative now. So I want to figure out when the second derivative is equal to 0. So if I set that in, I get 6x minus 12 equals 0. So if I solve this, 6x equals 12, x equals 2. So I have a change in my concavity, and it's going to happen at 2. I mean, a possible change. It doesn't have to change. So my sign chart is going to be broken into two intervals, negative infinity to 2, 2 to infinity. So I'll pick a test point. I'll see if the second derivative is positive or negative, and then I'll figure out if it concaves up or down. So I'm going to pick 0 for my point here, and then I'm going to pick, I don't know, like 10 here. So I will plug those into the second derivative. So f double prime of 0 is negative 12, so it is negative. And again, I'm just plugging it into the second derivative here. F double prime of 10 is going to be 60 minus 12, so 48, so positive. So this graph is going to, on this interval, concave down, and on this interval, it is going to concave up. So our final answer, so concave up from 2 to infinity, and down from negative infinity to 2. So if we want to graph it and kind of see what it looks like, we certainly can. We can just pull up Desmos and see what it looks like and see if the graph agrees. So my sketch, I'm just looking at Desmos, and it looks something like this. So it goes up, it goes down, and then it kind of goes up again. But the key thing is this is at the point of 2, which is kind of our breaking point. So you can kind of see to the right of 2, it does concave up. It looks something like this. And to the left of 2, it looks something like this. It's going down. So I would really encourage you to always check out what your graph looks like, because it should agree with the sign charts and the calculus we're doing. So here is a restricted interval one where we're looking at only the interval 0 to 2 pi, which we often do for trig functions. And we're trying to figure out what this concaves up or down. So again, we're going to need two derivatives. So the first derivative is going to be 1 minus sine x. And then the second derivative is going to be negative cosine x, because the derivative of sine is just cosine. So I'm trying to figure out where cosine of x, so I want to know where my second derivative equals 0. And I'm trying to find it on the interval 0 to 2 pi. So that's our unit circle. So if I think of my unit circle with my 4 special points here, remember cosine is the x value, so I want to know what points have an x value of 0. Well, that point would have an x value of 0. So that's at 90 degrees, or pi over 2. And this point down here would have an x value of 90 degrees. So that is 3 pi over 2. Now, there are other ones as the circle keeps going, but remember, we're only looking between 0 and 2 pi. So my sign chart is going to have pi over 2 on it, and then 3 pi over 2 on it. And we have these endpoints of 0 and 2 pi, because remember, we're only looking in that interval, 0 to 2 pi. So I have these three intervals, so I want to figure out where it concaves up, where it concaves down. And it's not required to change. Maybe it concaves up the whole time, but more than likely it's going to change. So I'll get my test point, I'll get my second derivative, a positive or negative, and then I'll talk about if it concaves up or down. So what are some good test points between 0 and pi over 2? I don't know, what about pi over 4? And then if I do between those two, I'll do pi, and then if I do between these two, maybe I'll do 5 pi over 3. Some angle over here in quadrant 4. So now I'll plug it into the second derivative, so I have negative cosine of pi over 4. So you can use the unit of circle, you can use your calculator. It's going to be negative. It's negative radical 2 over 2. So that's negative. So it's going to concave down in that region. At pi, it's over here. The cosine at that point is the x-coordinate, so it's negative 1. So negative cosine of pi is going to be negative negative 1, which is positive. So it's going to concave up. And then 5 pi over 3, cosine over here is positive something, so it's going to be negative of a positive. I believe it's negative 1/2, so it's going to be negative, so it's going to concave down. So it concaves up only on the interval between pi over 2 and 3 pi over 2. And it's going to concave down in the other two intervals, which are going to be between 0 and pi over 2. And again, you notice I'm using the parentheses for all these because they are open intervals. And then 3 pi over 2 to 2 pi. So besides having to use the unit circle, nothing too tricky about this. So we have graphed this function before, but we'll go ahead and graph it again and see what it looks like between 0 and 2 pi. So what I get when I sketch it, and I encourage you to hit pause, go ahead and graph this. Starts up here, and then it kind of arcs this way, and then it turns this way, and then it's going to turn back this way. That's pretty terrible. Let me see if we can do this better. So it kind of starts like this at 0 to 2 pi, and then at this point of pi over 2, it switches to something like this, and then a very subtle change at 3 pi over 2, it's going to kind of almost very slightly turn. If you didn't know the number 3 pi over 2, you probably wouldn't see it. So it's a very, very subtle difference as you change from concave down to up to down at 3 pi over 2. But again, I would encourage you, and remember, we're only looking between 0 and 2 pi, so that's the only region we have to look in. So those points where it changes is what we're going to call an inflection point. So we just talked about in that last cosine graph how it kind of changed from concave up to concave down. That's what we call an inflection point. So an inflection point is where the graph changes concavity. And that could be from up to down or down to up, doesn't really matter, but it's a change in the concavity. And so generally that's going to be where f double prime equals 0 if it changes. Because again, it is possible for the concavity to stay the same on opposite sides of a 0 of the second derivative. Most times it's going to be where that is. So we'll have to find second derivatives and everything else like we always have, make our sign charts and see if it changes. So f prime of x for this one is going to be 3x squared minus 2. And so f double prime of x is going to be 6x, just 6x. So when 6x equals 0, x is obviously happens at 0. So if I'm going to have an inflection point, it's going to happen at 0. So I'll do my sign chart based on that 0 of the second derivative, and I just want to make sure it does go from negative to positive or positive to negative. So if I pick some test points, negative 10 and 10, and I plug those into the second derivative and figure out if it's positive or negative, that will give me a good idea if I have concave up or down and an inflection point. So if I Then I get negative 60, which is negative, and I get positive 60, which is positive. So it goes from down to up. So we have an inflection point because it changes concavity. It's going to be at 0 and 3. Now, how did I get 0 and 3? Well, 0 I think is pretty straightforward because that's where it changes. That's the x value. So I'm really just plugging that x value into my original function. 0 cubed minus 2 times 0 plus 3. So that's where I'm getting 0, 3. So if I look at this graph, that is where it should change from concave down to concave up. That will be the point where it kind of switches. Again, something that's very subtle to see on a graph. Sometimes you can see it, sometimes you can't. It just depends on what your function is. So let's look at one more. This is a tricky one because we've got the undefined values again. So we have to find our first derivative first using our quotient rule because this is a quotient. So f prime, the derivative of the top, is negative 2 times the bottom minus the derivative of the bottom, which is just 1 times the top, all over g squared. Now the problem with these problems with the quotients, a lot of times you'll have to do this twice. So let's see, this gives us negative 2x plus 12 plus 2x minus 3 all over x minus 6 squared. Well, good news on this one, the x's cancel. And so this just simply becomes 9 over x squared minus 12x plus 36. So I went ahead and I FOILed this guy out because when I have to do a derivative again, it's better to have that FOILed out than kind of compact in there. So that's why I did that. So now f double prime of x, we're going to get the derivative of the top, which is just 0, times the bottom. So that's nice. Minus the derivative of the bottom, which is 2x minus 12. And then we'll have just the 9 for the function, so I'm going to put it in front. And this is going to be over x squared minus 12x plus 36 squared. So some interesting things usually happen for this. So what you'll see here is in the top, I'm actually going to factor out a 2 instead of distribute that 9. Because this happens almost every time. So if I take a 2 out of that parenthesis and put it with my negative 9, I get negative 18 over x minus 6. And now the bottom, if you recall, x squared minus 12x plus 36, that was x minus 6 squared. So now if I take that back to x minus 6 squared, I have x minus 6 squared squared. So the bottom is x minus 6 to the 4th. And why this is beneficial, and this happens so often, you'll see I can cancel a factor of x minus 6, and it makes my second derivative really, really, really nice. So I get negative 18 over x minus 6 cubed. So if I'm trying to figure out where this is going to be 0, it's never going to be 0. Now, if I was going to make up my sign chart, I would have to use negative 6 because that makes it undefined. But negative 18 on the top never equals 0. So this is never going to have an inflection point because it's never going to change. So because the bottom is undefined, it could change concave up and concave down. But if it does, it's going to do it at that asymptote and not at a point. So right away, I know there are no inflection points. So that is a benefit. And for these rational functions where you have denominators, that quite often happens where there is no inflection point. X. All right, the last thing that we're going to talk about is what's called the second derivative test. Now, the second derivative test is really a way to figure out if you have a maximum or a minimum value. So the second derivative test says this. It says if f prime of c equals 0. So I take the first derivative and I get a value that makes it 0. then if f double prime of c is negative, then c creates a max. And if f double prime of c is greater than 0, then c creates a min. Now, it's not very complicated to see why, so let's just do a quick little graph. So a derivative equaling 0 means it changed from increasing to decreasing. So at this point, I know it changes from increasing to decreasing. Now, if you look at the picture, that's obviously a max. But the reason is if this concaves down, then this has to be kind of at the top of the hill. So that's why it has to be a max. And over here, this is where it changes from decreasing to increasing, which we could do with the first derivative test. But since this concaves up, that has to be at the bottom of the hill. So nothing too crazy. So let's try an example where we figure out if we have max or mins. And I picked this problem because I think it's going to be kind of a tricky one to factor. So if I take the derivative, I get 55x squared, because that 3 comes down and cancels, minus 2x minus 21. And I'll also need my second derivative eventually, which is going to be 110x minus 2. So like I said, we're going to have to figure out when is 55x squared minus 2x minus 21 equal to 0. The nice thing about the second derivative test is I'll figure out a max and a min, and I don't have to make a sign chart. So I just have to figure out where these things are 0. So I have to factor this, which will be a little tricky. So if you don't want to factor it, you could certainly use quadratic formula. You could use your box method, whatever you do. So I know this is probably going to be 5x and 11x, although it could be 55 and 1. And so I believe it's going to be minus 7 and plus 3, because that multiplies to negative 21. So my check is there's negative 35, and there's plus 33, which is negative 2. So we have 5x plus 3 equals 0. 11x minus 7 equals 0. So x will equal negative 3/5, and x will equal 7/11. So the question is, will this be a positive or a negative in my second derivative? And that will tell me if it's a max or a min. So if I plug in negative 3/5 to the second derivative, I get 110 times negative 3/5 minus 2. I don't know what this is going to be, but I know it's negative because we have 110 times a negative number minus a negative number. That's definitely negative. So that's going to concave down, which is going to mean there is a max at x equal negative 3/5. And again, this is something you could graph and check, but I just want to use the calculus right now. And then I can do f double prime of 7/11, which is going to be 110 times 7 over 11 minus 2. So if I put that in, 110 divided by 11 is 10, so that's 70 minus 2, so that's definitely positive. So that's going to concave up, which means there's going to be a min at x equals 7/11. So this is a really easy thing. I didn't use any sign charts. Now, of course, I could graph and check and make sure it's a min or a max. But I wanted to show you we could do this without using the graph. So a little bit about concavity. Obviously, if you have questions about this, please let me know.